we attach them to our next projector, which is sponsored by the adult course foundation. And without any further ado, I would like to introduce Skylar. And the title of the research is Euclidean versus Non-Euclidean, and explorations of the importance of underlying assumptions. Yes, Skylar. So, as we get started, we need to go over some basic history of Euclidean geometry so we can better understand what will happen when we change the underlying rules of this geometry into new geometries. So, who has taken geometry in high school or middle school before? So that's the majority of it. So this form of geometry that you would have learned is called Euclidean geometry, and it was invented by a man named Euclidean, right there, in 300 BC. He wrote 13 books on the subject, which became known as the Elements. And the first book is very important to my research, and it contains 48 propositions and 5 postulates. A proposition is something that can be proven, or otherwise known as a theorem, where a postulate is something that is like an underlying truth or something that people just assume. The fifth postulate is very complex to be used as a different rewording of the Planck's postulate, which states that given a line and a point not on the line, it is possible to draw exactly one line through that point, which is parallel to the first line. This postulate and Euclid's fifth postulate, as they're the same thing, was very unlike by the math world as it was so unlike the other four. People sought to add it to the proposition list since it seemed more fitting, but had no basis to do so as they could not prove that it had a conclusion itself. Instead, mathematicians Gauss and Bollier came up with new mathematics that excluded the fifth postulate altogether. These were called non-Euclidean geometries because they did not follow all of Euclidean's postulates and rules. And examples of these are hyperbolic and spherical. But before we can get into those, we talk about the research question. So all of this history led us to question what would happen to the different objects in geometries, like lines, angles, and shapes, if you change these underlying assumptions. But before we begin, we need to talk about some definitions to generalize the terms that we're using. So circles are going to be all points equal distance to the center. Parallel lines are going to be two lines that never intersect. And geodesics are the shortest path possible between two points, so point A and B. And a shear quadrilateral is a special quadrilateral invented by an Italian mathematician named Geometries, which can be constructed from drawing a base and two congruent sides at 90-degree angles to this base. When these are drawn and the top is constructed, the two top angles, or these two summit angles appear in Euclidean geometry will hold to be 90 degrees, but this is going to change in the different geometries we'll look at. And a proof of this includes cutting the quadrilateral into two equal triangles. And since we know that all triangles have angle sums equal to 180 degrees, we can say that this whole quadrilateral has a 360-degree angle sum. Since two of these angles we already know to be right angles, that's accounted for 180 degrees. And since we know that these two lines are parallel, these two angles also have to be the same. So you can divide the remaining 180 degrees by 2, getting 90 degrees. The first geometry we'll look at is spherical geometry. Spherical geometry holds a difference in the way parallel lines are, which can be found when we worded out of the Planck's postulate to state that given a line and a point not on the line, it is possible to draw no lines through that point that are parallel to the first line. And basically it just states that there is no parallel line. And this can be modeled on a sphere. So the first thing we'll look at is lines, which are basically extensions of geodesics. So these two, this line model here on the picture is a geodesic as the shortest point line possible between those 2 points. And if it was extended around the sphere, it would create a big circle that would cut the sphere equally in half. This is known as a great circle, and from now on, great circles and lines are going to be equivalent terms. So in our exploration, we found that there are two different kinds of circles, great circles and lesser circles. Great circles are modeled in green and lesser circles are modeled in red. And the lesser circle is any circle that's not a great circle, so any circle that doesn't cut it exactly in half. And these can be created in two ways, by either cutting into the sphere with a plane or cutting into the sphere with another sphere. Next thing we'll talk about are angles. We will use Euclidean units of angle measurements of degrees or radians, but because we're using Euclidean units, we also have to use Euclidean methods of measuring angles. And that means that we have to measure an angle between two straight lines. But as we talked about, spherical lines are curved, so we can't measure the angle directly. Instead, we have to create a tangent plane to the angle at a point. So say we're measuring angle alpha. We put the point on the vertex C of angle alpha and create a plane that's tangent to the sphere at that point. Then we draw the line that's related to the line of the angle and measure the angle in between those two lines and call it the spherical angle alpha. Another thing to look at are propositions. So because of the small scope of this project, we're only able to view propositions 1 through 32. And we tried different examples on the sphere, purposely trying to find a counterexample and 2 tries. If we couldn't find a counterexample to each proposition, we deemed it possible. And if we did find one, we said that it could not hold 5 groups of counterexamples. In empirical geometry, we found counterexamples to 3 propositions, 16, 17, and 21. And we also found that the triangle angle sum proposition, or proposition 32, can be reworded to state that given in empirical geometry, the sum of all interior angles of any given triangle are equal to greater than 180 degrees and less than 540. This can also be seen on the sphere, as these angles are clearly going to add up to more than 180, as most of them are obtuse. But this does not mean there cannot be 2 angles on the sphere. It just means that there is a possibility of obtuse angles. If we have more than 2 obtuse angles, we can already say that's a counterexample to the proposition, and that would need to reword it. Last we looked at are Shishiri quadrilaterals. And Shishiri quadrilaterals are going to be constructed the same way, but their summit angles are going to add up to be greater than 90 degrees. This is because, again, as lines curve, they're going to create obtuse angles at the top instead of acute angles. This can also be seen with the same proof. If we cut it into 2 triangles, if we know that both the triangles have to have sums greater than 180 degrees, then we can say this whole thing has a sum greater than 360 degrees. So then when we take out the 180, there's still greater than 180 left. So we have to say those are going to be greater than 90. Next geometry we looked at is hyperbolic geometry. Hyperbolic geometry is also holds a change in the function of parallel lines. But this time it can be reworded to state that given a line and a point on the line, it is possible to draw infinitely many lines through that point which is parallel to the first line. And this can be modeled on a concrete disk. Now, so this is a concrete disk up here, and actually every single fish on this disk is exactly the same size. So this red fish right here is the exact same size as that tiny little blue fish over there. So anyone who does not know how this works, can they take a guess at how this might be possible? Jay? Yeah. It's not really go. Anyone else? Not quite. Not magic. Okay. No. Either yoga. It's actually not 3D, it's a 2D shape. And is it? No. Well, that changes how parallel lines are, and so technically, yes, but there's a different answer that I'm looking for. So if you're saying that would work on a 3D shape, like a sphere if you're looking at it, but the problem is it's not 3D, so that doesn't quite work. Okay, so actually, it's because distance is being so distorted around the edges that it's making everything visually smaller. So around the edge of the disk, distance is actually going to be, the points on the edge of the disk are going to be infinitely far apart. So the closer you get towards the edge, the more distance is distorted. So the center distance will be almost normal, but on the edge it's going to be so distorted that things can look smaller even if they're the same size. So we're going to look at lines again, and lines have two types in hyperbolic geometry. It would be diameters versus circle intersections. Where diameters are going to be something like a blue line, which cuts straight through the disk. And circle intersections, as well as these red lines, are going to be where circles literally intersect the disk at right angles. The next thing we'll look at are circles, which are not going to be of two types, but they're going to look different based on where they're located. So a circle in the center of the disk is going to have distance being distorted around it equally, so the center visually stays in the middle. However, when it gets close to the edge, like this blue circle, distance is being more distorted toward one of its sides, which visually pulls the center over, even though all points are still the same distance away. Angles, we are again going to measure a median with units out of degrees per radian. However, we still can't measure them easily. Well, we can't measure them directly because they're still curved. But since this is a 2D shape, not 3D shape, we're not going to use the same method of using a plane, but rather we're going to draw lines that go through the points that are tangent to the curves and measure the angle in between them. For the propositions, we did a similar method and tried to find counterexamples, and we were able to find counterexamples to two of them, 29 and 30. And the triangle angle sum theorem we reworded to state that the sum of all interior angles of any triangle in hyperbolic geometry is going to be less than 180. This could be seen in this example where all angles are acute angles. This again does not mean there cannot be obtuse angles. It just means that we found one example in which all the angles do not add up to 180. So here's the counterexample. And then when we further explored, we found that none of the triangles can add up to 180. Because of how lines are curving, it creates a smaller angle measurement of these angles. So when you add them up, they cannot be as big. And then now we look at exterior quadrilaterals again. And their kind of angles, just as we change the triangles, are going to be littler, so they're going to be less than 90 degrees. This can also be seen as a kind of standard again. Since the triangles have a littler sum, we have to say that the angles are also going to have a littler sum. And this can visually be seen by the way this angle is smaller because of the curves of the line. The last geometry we looked at was taxicab geometry. And taxicab geometry arose from this, taxicab system. So if you're in a taxicab going through the city, you have to take the street. You can't go straight through a building or straight through a skyscraper. In this way, you also can only take horizontal and vertical movements on the coordinate grid and can't go straight through. So this is a change in the assumption of distance. Instead of using a Euclidean distance formula, we're going to use this distance formula, which basically is the sum of all the x movement and the sum of all the y movement. And this can still be modeled on a coordinate grid. So lines in taxicab geometry are going to be very different as they cannot be extended. They cannot be extended geodesics. From getting to point A to point B, we found three different routes: the green route, the blue route, and the red route. Each one of them are of equal length. The problem then arises as all of these are geodesic at point A and point B. So if you were to extend the line AB, you wouldn't know which geodesic to extend because they're not unique. Therefore, we are going to use Euclidean lines as the lines for our taxicabs, but still measure them based on the distance formula of taxicabs to the horizontal and vertical movements. Tactical circles are going to be very weird, as they are known to be a square. So this right here is a tactical circle with a radius of 2. So the black line would be a radius line, but then this green line and the pink line are still 2 units. So you take in their x direction, which would be 1, and their y direction, which would be 1, still adds up to 2. If you were to do this about every point on the circle, you'd still get the same length, which is all points equal distance. Angles are also going to be measured differently, and they're going to take on the unit of a tactical radian, or a T radian for short. Because of direct conversions and some indirect conversions, the direct conversions included 2 T radians being equivalent to 90 degrees and 4 T radians being equivalent to 180 degrees. However, acute angles like 1 T radian do not have direct conversions, so you cannot say 1 T radian equals 45 degrees. Instead, there's a very long, complex formula that we can use, but it's really long. So the next thing was that we're going to have propositions, which we've got counterexamples, 10 of them, which were 4 through 6, 18 through 21, and 24 through 26. And many of these change because of the way that triangles are also not unique in their measurements, because we can change how triangles look, even if they measure the same with their length. And the triangle angle sum proposition can be reworded to state that in tactical geometry, the sum of voluntary angles of a triangle are equivalent to 4 T radians. And we already know that 4 T radians are equivalent to 180 degrees. This does not change, it just takes on the different units. Last thing I looked at was Shapiro quadrilaterals again. And even though, and since they're constructed the same way, these lines are going to still be parallel. And parallel lines have the same slope, which means that both of these lines have the same Euclidean distance. And because they have the same slope, we can also say that their x direction and their y direction are the exact same. Because of the slope formula, which is rise over reference, we know they have to be the same. Because of this, we can say that these lines are both equal in the Euclidean distance and tactical distance. So when the top is constructed, we can say that the sum of angles are going to be equal to each other. And because we know that these are going to be perpendicular, we also know that these are going to be perpendicular. These are going to be right angles. The only reason we don't say that they're still going to be 90 degrees is because we have the new unit, so we call them 2 T radians, which again are going to be the same thing. So here are my references that I got. And if you notice, most of the other references for the pictures were on the slide with the pictures. And for this project, I'd like to thank the Frontiers of Science Institution and UNC for hosting it. And I'd also like to thank the Adolf Force Foundation for funding this project, and Samantha Moore, my mentor, and David Saad, my advisor. And I'd also like to thank Lori Ball for being the director of this program and the entire FSI staff. And if we have more time, we can talk about this equation. So this is a very nice equation, but to be simplified, this is how you get from T radians from the acute angles. So basically, you look at the reference angle, so the angle from the x-axis. So whichever coordinate you're in, you can just find that angle based off the x-axis. And then you can plug it into this equation and basically just spits out your answer, so it's pretty nice. But you wouldn't want to do it by the end. So, any questions? Oh yeah, okay, so for spherical geometry, we used a physical sphere. So just clear, and then we just took wet erase markers and drew on it and used rulers and stuff. And for hyperbolic, we used a program called Non-Euclidean, which basically you can just draw the different shapes on it, and it calculates all the distances and your angle measurements. It's really nice. And then the tax tag is Geometries, which I think most of you are familiar with. So,
So it's a little goal, for instance, you know how a lot of all maps and classrooms are not accurate because countries near the equator are the shortest. So like Africa is smaller than not so you're sorry. I'm sorry. Continent countries near the poles are the shortest and they're a lot smaller than next question.
Straight back the circumference and make it all half the center. Is there a way to calculate how much
yes. I don't know how though, but there is. I'm not sure.
Sorry.
We didn't really do that much about it. We just knew that it's historic, and so we were trying to form logic through what happened while it's historic. Like, what would it change? Yeah. Trisha?
So in Euclidean geometry, there's obviously like a protractor that can like measure the angle. How do you measure the angle in non-Euclidean geometry? Is there like a physical medium?
Well, it's different. Like for spherical geometry, we still had to draw the plane, which would still give you that angle. So you could still like use a compass on that plane. You had it, and like it would be like putting a piece of paper on a basketball, and then draw an angle off of that. In the hyperbolic, you just still draw the lines and measure it the same way. So it's pretty easy to measure angles. In tachygraph, it's actually more complex because you have to put the unit circle on it and measure the length of the arc. So,
do you know like some applications
there are two, like in spherical, obviously the world's a globe, so everything's not going to be Euclidean lines on sphere in our real world. So we can use things like spherical for that. Or in like taxicab, I guess you could say it can help you like plot better paths for a taxi in city.
What's your most exciting?
I think one of the most surprising, for example, and I don't quite know the proposition, but in one of them we created a triangle that was 160, 160, 170 in spherical. And when we were just getting started, it was pretty mind-blowing, like, oh wow, you can create a 302 angle triangle. Or like hyperbolic, and we were doing something, we created a triangle with an angle sum of less than 0.1. So that was pretty fun too. Any other questions?